All right. Good morning, everybody, or good afternoon, good evening, wherever you are. Welcome to the Zeus Town Hall meeting for finding out information about the facility commissioning status and our second call for proposals for the financial year 2025. All right. Ooh. So in this town hall, we hope to go through a number of things with everybody. We will introduce the laser system itself and talk about the target areas that we have available and the different types of flavor of science that we expect to be performed in each, although you may have entirely your own ideas. We'll present about the Zeus commissioning and status of the facility. I'll go over the capabilities we hope to have available for the second year of operations. And then at the end, I'll talk about how users may access the facility and what the proposal process is to actually apply to perform your experiments here. I'll begin with just introducing the Zeus team. I haven't got photos of everybody, but there are a lot of the people involved up here. Carl Kruselnik is the director of the facility, and we have many other people involved from both the laser side of things and the experimental side of things that you might get to interact with. Okay, so starting at the beginning, Zeus is actually an acronym, the Zettawatt Equivalent Ultra Short Pulse Laser System. And that's because a zettawatt, which is an extraordinarily large power, if you had a zettawatt pulse, you'd be able to reach the critical field strength where you could achieve vacuum breakdown and get spontaneous creation of electron-positron pairs. We only are going to be producing 3 petawatt power pulses, and although this will make it the highest power laser in the US, it's still orders of magnitude below the zettawatt power, and therefore in order to get the equivalence, we perform a trick. We use part of the laser pulse to accelerate a very high energy electron beam and counter-propagate it to a very high intensity laser pulse, so that in the rest frame of reference of the high energy electron beam, it will see the equivalent field to that of a zettawatt power pulse. So that's kind of the signature experiment that the facility was designed for, but there's many other potential experiments that can be performed in this high field regime as well. And the facility was recently opened. We had a grand opening celebration with many visiting scientists and speakers coming to celebrate with us. And now it's down to the hard work of operating as a facility. So just to introduce you to the facility, there's a floor plan shown here. For scale, there's a person in this top right-hand corner. The first thing is this yellow region here, which is the laser clean room, and it houses the laser and the compressor chambers. We then have 1, 2, 3 target areas for the experiments to be performed. We have extra rooms like the experimental control room and target preparation areas and diagnostic preparation areas that the experimenters can use as well. And just to show you that these are really here and ready to use, we've got some photos of the different spaces shown here. I'm going to go through all of these in more detail now. Now, starting with the laser itself, it all begins with a front end that was supplied by Amplitude Technologies. This is a double CPA system. So we start with our oscillator at a very high repetition rate. The pulses get stretched, amplified, reduced in the repetition rate is reduced. The spectrum of the light is adjusted, and before we have another amplifying stage, the pulse is compressed and it goes through an XPW module, which cleans the contrast of the laser pulse. We then re-stretch the pulse, and it has its spectrum adjusted again. It's then amplified, reduced to 5 Hertz frequency, and it's amplified once more. Then we have one more stage of the front end, which is a final amplifier, which outputs 1.5 joules. We then take this 1.5 joules and we go through another 1, 2, 3 main amplifying stages. The beam diameter gets progressively larger and the amplifying crystal size gets progressively larger with each of these stages. The aim is to get 120 joules out of these 3 amplifiers, so that when compressed through one of 2 compressors we have available, we can either get 75 joules in 25 femtoseconds, giving us the 3 petawatt pulses, or the second compressor can achieve 12.5 joules in 25 femtoseconds, giving us half a petawatt. Okay, so this is the design of the final system. We have a slight difficulty with the first year, is that the final amplifying crystal is not yet available. This means in our first year of operations, we are running the system with a reduced diameter final amplifier, which limits us to 25 joules in 25 femtoseconds, or 1 petawatt operation for the first year. The second year of operations, which we're about to make the call for proposals for, we should have this crystal installed, and we're aiming to run at 2 petawatts, 50 joules in 25 femtoseconds, potentially 3 petawatts, but we'll be ramping up cautiously. Okay, so how does this all fit into the facility? We've got another kind of map of the facility here. So in this laser clean room space here, we start with our front end in this bottom left corner. It then goes through the 1, 2, 3 amplifying chains to give the pulse energy. You can see the pump lasers here in the center of the photograph, and the amplifying chain is inside this enclosure here. After we've amplified the pulse, we can send the pulse either to this 3 petawatt compressor with the very large gratings, the chamber is shown here, or we can send the light over to this 0.5 petawatt compressor. The other option we have available is to split the energy, split the pulse with a beam splitter, sending part of the light to the 3 petawatt compressor and part of the light to the 0.5 petawatt compressor. The laser has several diagnostics that can either run on shot or off shot to monitor the pulse. Each shot will be given a timestamp to identify that particular shot. We'll have on-shot laser energy measurement, on-shot beam profile measurement before and after the compressor from leak-through mirrors. We'll have on-shot laser focus monitoring from the leak-through as well. And then off-shot, we'll be able to take pulse duration measurements with autocorrelators, frogs, and self-referencing spectral interferometry. And we'll also monitor the laser spectrum. We then also have 2 deformable mirrors, one in air and one before in air before the compressor and one after the compressor. And we have off-shot laser focus and wavefront measurements. This is set up in target area 3, but we have plans to set that up in other target areas as well. And then finally, in terms of the laser capabilities, we have a modest long pulse capability. We're calling this a shock driver laser. We're planning for this to be available in target area 2 for the second year of operations. It's a commercial system, an amplitude intrepid laser, a neodymium glass system. Its fundamental wavelength is around a micrometer, or could be doubled to into the green. We can operate this at a shot per minute, and it can output depending on the pulse duration. So we can adjust the pulse duration, and so at a long pulse duration of 10 nanoseconds, you might be able to output 110 joules of red light or 75 joules of green, and then at 1.5 nanoseconds, you might be able to output 46 joules of red or 35 joules of green. And the idea behind this is you might be able to do pump probe experiments where you use the long pulse laser to drive an interaction, maybe a shock in a target, and you can then use the short pulse part of Zeus to probe through generating particle or light sources to probe that on a very short time scale. Okay, so that's the laser stuff. Now we can take the light to different target areas. So the first one, target area 1, this is our signature target area. I'll come to the science in a moment, but we can send the light either from the large compressor here into the chamber. We have in the chamber a deformable mirror to correct the wavefront, and then a very long focal length, a 19-meter focal length parabola to take the light to the interaction point, which it will typically might be a gas cell for laser weight field acceleration. I'll come to that in a moment. We also have the option here to take the second compressor pulse. Again, we have another deformable mirror for that line, and then we're having a short focal length over here. So the target chamber is in place. We have a lot of local radiation shielding. You can see over here we call it the cave, to contain the multi-GeV electrons and the associated radiation we anticipate generating. And to go into more details about the configuration we hope to have available for the second year of operations in this area, we're hoping to offer 2 petawatts with the long focal length geometry, or you could split the beam and have 1.5 petawatts and half a petawatt. The 1.5 petawatts would be on the long focal length parabola, and the half petawatt would be an F3 parabola with a 75-degree off-axis angle. Okay, so in this area, we have a couple of semi-permanent diagnostics. The list will probably increase once we have things set up. The main ones are a triple magnet electron spectrometer designed to measure the multi-GeV electrons, and we have plans to install an optical probe beam. Okay. The flavors of science that we anticipate in this area would be based around weight field acceleration of electrons with that very long focal length. This is a kind of cartoon of how an experiment would look. So we could accelerate electrons in a gas target, remove the residual light with a tape drive, measure the electrons with magnets. These magnets can move in and out depending on whether we want to measure them or use them for our experiment. We can refocus them to perhaps have a collision with the high intensity laser pulse coming from the other direction. Ignore the F number in this cartoon here. Then we envisaged we'd be able to measure the products using an electron positron spectrometer and also monitor the photons coming out. That would kind of be a signature experiment setup. Other people might have different ideas about what they want to do. You might use the electron beam to produce very high energy photons and do an experiment in that way as well. So we don't want to be restrictive. This is just how some of the experiments we envisage. All right, target area 2. This is our second target area. It's a similar size to target area 1, and it has 2 feet thick concrete shielding as does target area 1. Eventually we'll be able to go to 3 petawatts in this area, but we are currently restricted due to the chamber size to half a petawatt. We hope to be able to offer half a petawatt in this area for this second call for proposals. The unique thing about this area is we have a double plasma mirror setup, a deformable mirror, and short focusing configuration. This means that we can reach the highest intensities with the highest contrast pulses. In this area, the semi-permanent diagnostics are a Thomson parabola ion spectrometer, and we have many interchangeable diagnostics that are available as well. The types of experiment we envisage would be to do with interactions with solid targets, typically, because we have very thin solid targets. We shouldn't have too much pre-plasma. This might lend itself to proton and ion beam acceleration or neutron generation, gamma beam generation through various mechanisms, or high harmonic generation. Again, this isn't an exclusive list. You can do what you like with the pulse, but these are the kinds of experiment we expect. And then finally, target area 3. This is the furthest along. There are actually experiments taking place, or commissioning experiments taking place already in this area. We have demonstrated 200 terawatts at a 1 Hertz burst operation mode. If I remember correctly, we've had up to 20 shots in the Hertz burst mode. We're kind of restricted because if you go into a burst mode, you start to change the pulse properties and lengthen the pulse. So we envisage limiting the burst mode to around a 200 terawatt operation. In the second year of operations, we're hoping to offer the full half petawatt at a shot per minute into this area. The beam diameter in this area is only ever going to allow us to go to half a petawatt. We hope to ramp up to this full capability. We have significant concrete shielding around the area for radiation shielding, and we have 2 different focusing geometries available, F40 and F20. So looking at this schematic over here, we have the laser pulse coming in from the compressor. We have a deformable mirror. The light is then taken. It can go to the F20 or the F40 focusing geometry to parabolas to go to the interaction point, which is typically a gas cell over here. We then have a number of semi-permanent diagnostics. This is, like I said, this is the best developed area, so it has the largest number at the moment. So we have the magnetic electron spectrometer. We have an electron beam profile monitor, and an X-ray CCD, which is an Andor sitting over here, that can be used for imaging or single hit spectroscopy, depending on your experiment. We then have, we monitor the laser focal spot, we take laser wavefront measurements, and we look at the laser pointing. And then finally, we have an optical probe beam setup. We pick off light from a thin pellicle here, and we have various delay lines, which sends the light across the interaction point here and out to the diagnostic table. We have interferometry and shadography set up over here. All right, so the types of science in target area 3, again, they're mainly based around laser wake field acceleration of electrons and the high energy photons, the betatron X-rays that might be generated, and then the applications of those particles and photons. We're also hoping, once the sources have been properly characterized, to offer these to non-traditional high-power laser users, for example, to look at material science or for medical imaging applications might be possible. And then I've already talked a little bit about some of the diagnostics. I've mentioned some of the semi-permanent diagnostics we have in each of the areas. But we also have a broad selection of movable diagnostics that will also be available for use. Information about these diagnostics is available from a link on the Zeus website. Some of them have more information than others. This is a work in progress. We've been mainly concentrating on getting the facility ready, but we hope to make more information available as it's edited and produced, let's say. But if you have a question, you can speak with us to get more information about specific diagnostics. And you might also have your own diagnostic you wish to integrate into the Zeus system. We are here to provide mechanical and electrical engineering assistance to help you do that. So please contact us if you have questions about that as well. And then targets is another essential part of experiments. We have Sally Klein, who is a target fabrication engineer, who's leading the efforts to assist with target preparation. We have available a suite of instruments for characterizing targets. They're actually located in a room right next to the experimental control room. We have some basic targets available to users: flat foils, gas jets or gas cells. We have a variety of designs and gas types, and these are potentially adaptable depending on what you want. We have two-stage supersonic gas jets or two-stage variable length gas cells, and you can change the gas type that you're requesting there. And we hope to be able to commission a liquid jet target. We have these available in the Centre for Ultrafast Optical Science. We just haven't commissioned them in the Zeus area yet. So contact us if you're interested in that kind of target. We know that the community has many other target needs, and we hope to be able to offer some specialised target fabrication in-house, or we might be able to use outside vendors for some of the parts. But we do need to perform a cost analysis before we commit to any of these more advanced target types, because we know they can be very expensive and we have a very limited budget. But contact us if you're interested in that. So back to the commissioning status. About what the laser has produced so far. The front end is performing well. We get 1.5 joules as expected in 20 femtoseconds. That has a 90 nanometer bandwidth, and it runs at continuous 5 Hertz. The first phase of commissioning has been completed. We've achieved greater than 200 terawatts, and that light can go through to target area 3. So the compressor has output 6 joules. And the measurement of the light implies a 26 femtosecond full width half maximum pulse duration. The bandwidth of the output compressed light is 80 nanometers, which is slightly reduced from the front end as expected. The light has been focused. You can see a screenshot over here. The light has been focused to achieve a Stirl ratio of 80%. Using the deformable mirrors to correct the wavefront. The pulse has a better than 2 femtosecond computed radial pulse delay, and the pointing jitter is around 1 spot diameter right now. And I mentioned before, it has been run in a 1 Hertz burst mode up to 20 pulses. Running to 20 pulses does lengthen the pulse duration a little bit, so we have to be cautious when we're going into burst mode to not degrade our pulse too much. And then finally, I've got a photo of the amplified beam profile taken at the compressor input. All right, how am I doing for time? So the capabilities for the financial year 2025, the second call for proposals, are given on this table. So this is a little bit detailed. On the left-hand side, we've got the parameters that I'm talking about, and then we have for each of the target areas, 1, 2, and 3, we have what we're aiming for in our first year of operations, what we're aiming for in our second year of operations, which is the call for proposals that's just coming out, and then what we eventually hope to achieve in the different target areas. So the blue one is the second call for proposal, the one we're about to announce, that you should look to what we're hoping to offer. So in target area 1, we hope to achieve 2 petawatts in 50 joules in 25 femtoseconds at a shot per minute. You can use the beam as a not split option, 2 petawatts straight, or with you can split to 1.5 petawatts and 0.5 petawatts. There's no plasma mirror available in target area 1, but the focusing options are the long focal length, the f64 with the full 2 petawatts, or if you're operating in split beam, the 1.5 petawatts with the long focal length and the 0.5 petawatt with the short focal length. And then we're not anticipating offering the long pulse into target area 1 in the second year of operations. Target area 2, we're hoping to offer half a petawatt with 12.5 joules in 25 femtoseconds at a shot per minute. We don't anticipate a split beam option in here, and the chambers are little small, so that will have to wait for the larger chamber, but we do have a double plasma mirror option in this area, which will clean the contrast of the pulse. It's going to be an f2 focusing, a short focal length to achieve the highest intensities, and we hope to be able to offer the long pulse in this area for the second year. Then target area 3, again, we hope to reach the half petawatt with 12.5 joules in 25 femtoseconds, with a shot per minute for the half petawatt. If you would like to try the 1 Hertz burst mode, we hope to be able to do that at 200 terawatts. There will be no split beam and no plasma mirror in this area, but 2 different focusing F40 and F20 available. And for this year, there will be no long pulse available in that area. Okay, so now you've heard all about the different capabilities of the facility. We obviously have the option for you to access the facility. And so this is just some information now about that. So we'll have annual calls for proposals. We successfully had our first call, it closed, we've allocated the time, and now we're opening the second call for proposals for the financial year 2025. So once the proposals come in, they're sent to the proposal review panel. This is an independent panel separate from the facility. No members from the University of Michigan, the Zeus facility, or the Center for Ultrafast Optical Science are on this review panel. So the proposals really are assessed for the best science. They'll be looking for granting access for fundamental research in physics, medicine, and engineering, rather than industrial or commercial experiments. I.e., we want you to publish your work, and no classified research will be conducted using Zeus. It does not matter where you are funded from, however. We're National Science Foundation funded to operate the facility, but it doesn't matter who funds your research for the experiment you want to perform, so long as it's good science. Successful proposals will be passed back to the Zeus facility for scheduling, and each experiment will be assigned a link scientist to help them initiate the planning process for the experiment. The users will then connect with the Zeus user office to arrange their training before arrival, and I'll tell you a little more about that in a moment. Users, we hope that you'll, as users, provide us with constructive criticism and feedback so we can improve the facility. Just in terms of initiating and planning your experiment, we anticipate this to be done a few months ahead of time, at least 3 months ahead of time. We'll start experiments to initiate the first planning meetings to identify elements of the experimental design that require development and to order targets. Second meetings to finalize the experimental design, review for conflicts, design or operational problems. And a couple of weeks out, we'll have a final planning meeting to finalize all of the experimental elements. And then we anticipate users can arrive before their scheduled shot weeks to set up their experiments. And I'll also note that all of the users register through the MyZeus portal. I'll come to that in a moment, and can coordinate with the user office to initiate their travel plans and take the required safety before they arrive at the facility. A typical experimental day would look something like this. The laser will be warmed up by people arriving early in the morning before the users, we anticipate. then we'll have a morning meeting, a quick morning meeting with the users to discuss what will happen for that day. We hope to make the laser available mid-morning to the users, and then we'll switch the laser shift around lunchtime so that we can operate through the afternoon and into the evening, switching off the laser in the evening so that everybody can close the laser down and go home. So while an experiment is running in one of the target areas, other target areas can be working on setting up their experiments and planning that. Okay, so the second call for proposals is about to open. This will be for the financial year 2025. The announcement is about to go out to the Zeus user group email list, and it will be posted on the Zeus website, and we'll post it to as many other places as we can find. The proposals will be due through the online submission system by 5 p.m. Eastern Time on the 31st of January 2024. And the expected capabilities, the ones I went through today, will be posted on the Zeus website. So approximately equal number of experiments will be scheduled in each of the target areas. We don't want to run entirely in target area 1, for example, because we need to spread the load so that we can adjust the setups, etc., in that off time between experiments. We envisage typically experiments would be about 4 weeks long, although you might make the case for a longer run if it's more complicated, or shorter run if it's a simpler experiment. So you should justify that in your proposal. And the eligibility criteria is we welcome proposals from the whole scientific community, from both within the plasma physics community and beyond. There's no restrictions on your funding support. So Zeus is funded by National Science Foundation to provide the facility time, and then you can be funded by whoever to do your research here. International researchers are welcome to submit proposals for the facility as well. We want the best science. Okay, so the My Zeus portal. This is a web-based user interface to the facility. You can see the landing page here, and you can see I've not logged in or registered as yet on this page. So as a new person, you would come to this page and click on register. This will take you to a simple bit of information, I think your name and your email primarily. You'll be emailed a link to confirm your email, and then prompted to ask for more details about yourself. Once you have registered, you can log in, and then you're eligible to do a few different things. So for example, you'll be able to click on this panel, and there's then a link to submit your proposal, and that's how you would do that. We also have information about the laser status. Once you have experimental data, that will be available through My Data. We hope to be able to offer some open data once we have taken it. We have a link for experimental planning, a link for lab resources like diagnostics and configurations, etc. will be here. We have a calendar for the experimental schedule, and things like registering and things about your user account will be available here. And then there's a link to see the contacts within the facility itself. I will note that My Zeus portal is a work in progress, so please help us out and let us know if you encounter bugs or problems. We know that there will be some, but we can't fix them if you don't tell us. So we hope that you'll be able to help us out here. Okay. So the first thing, if you want to submit a proposal, is to register for a user account on My Zeus portal. And then you'll need to prepare your proposal according to the requested proposal preparation guidelines. These are available on the Zeus website. They are pretty much unchanged from last year. If you have any questions, you can contact this email address that comes through to a few of us here at the facility, and we'll try to get back to you with answers, or put you in contact with a person who can answer as soon as possible. I'm also going to schedule a couple of question and answer virtual sessions so that you can call in and speak with the Zeus team over the next month or so. Particularly, I note that this isn't a particularly friendly time for the West Coast, so I'll schedule them at different times of the day to be accommodating for different time zones. And then you'll submit your proposal through the MyZeus portal before the 31st of January 2024. That should be at 5 p.m. Eastern. I'll correct that for when it goes out. Okay, so that brings me to the end of my presentation. I would welcome any questions that people might have now, and we'll close this down so that I can see you all. Do this first. All right. If you would like to unmute and ask a question, feel free. If you would like to ask your question in the chat, that's absolutely fine as well. Hello. This is maybe a question for John, a question about the contrast, the intensity contrast.
Sure. If everybody can hear me, I'll just answer. The contrast of the laser was measured at the front end pulsar module by amplitude to be with a 10 to the 7 contrast in the nanosecond time scale, and 10 to the minus 11 contrast in the picosecond time scale. So from the nanosecond pulses that can be caught by a Pockels cell to the several few tens of picoseconds range. This is the range where we have about 10 to the minus 11 contrast. And then as we go into the picosecond range, from about 30 picoseconds to the third order correlator limit around 30 to 50 femtoseconds, there's exponential growth from 10 to the minus 11 to 10 to the minus 7. And so the contrast in the nanosecond time scale is considered to be an energy contrast, and the contrast in the shorter time scale is an intensity contrast.
And then I'll just add to that, after the laser system, if you go into target area 2, we have a double plasma mirror system, which will clean the contrast further, particularly removing a lot of the ASE and some of the picosecond contrast as well. Does that answer your question?
I'll bring in one more point about the third order correlation. We do have a third order correlation, but we have not yet applied it to the amplified signal from our from the first amplifier stage that was described in the laser layout. So we have yet to do the amplified third order correlation measurement.
And the double plasma mirror improves the contrast by 3 orders or 4 orders of magnitude, typically. So, with the caveat that the energy goes down by a factor of 2.
Lottie, do you want to unmute and ask a question?
Yeah, thanks, Louise, for a very nice presentation. I was wondering if you had any plans for circular polarization for the future?
Maybe I'll field that. We have a 4-inch quarter wave plates that have been applied to the beam in the past. 100 millimeter diameter is the outer diameter of these mica wave plates. That's the capability that we have in-house. These are uncoated, and their wavefronts are not terrible, but they're not great.
So those
Thank
have been used before in on the Hercules facility, and there's some published data from using those wave plates.
They would be available in TA2 and TA3 up to 500 terawatts. Well, we'd have to see how far they would go. I think there's also a half-wave plate. Is that not right?
Yeah, we do have multiple copies of both half and quarter wave.
Okay, there's another question. Is radiochromic film available in target area 2? Well, we can certainly use radiochromic film. At a shot per minute, we're starting to look at alternatives. So particularly, we're looking at scintillator detectors for the protons, like proton beam monitoring. But certainly, we can use radiochromic film in target area 2. It's just a question of how many shots we can take before we need to let up the chamber. It might not be terribly efficient. Oh, there's a question, Manfred.
Hello, thank you for an excellent presentation, Louise. Can you comment on any pulse structuring methods you might use, either spatial structuring, temporal structuring, or spectral structuring of the pulses?
That's probably another question for John, I think. I'll work on that one. The system is equipped with, first of all, the laser is a double CPA system, and the first CPA is hidden behind the XPW and is responsible for giving good contrast. And while that has a dazzler phase device in it, we don't really use that to operate the laser system. The second CPA has the petawatt stretcher, and it also includes a dazzler, which is an acousto-optic programmable phase delay device. And so it operates over a total range of about 3 picoseconds. And we use that device to obtain the shortest pulses we can in combination with a fast light Whistler, which is a spectral self-referencing spectral interferometer. I know it's a lot of technical terms that most people aren't familiar with, but those are the devices in the system. And the dazzler can be modified, modifying the second order phase to get chirp of one sign or another, modifying other orders of phase can be done. We need to approach that with caution, because if the dazzler were to send a narrow spectrum through our amplifier, the chirp pulse amplification scheme would be defeated and we could damage a lot of optics. I think another thing if you have something in particular you would like to attempt, to contact us now or ahead of your submitting a proposal would be helpful, so we can give you some feedback on that to say if what you're hoping to do is possible or not.
Awesome. Thank you, everyone.
I do want to make a comment that Louise covered some of the temporal pulse shape elements of the laser. She went through the information with respect to the amplified pulses that we've had to delivered to the laser system. The best measurement of pulse duration we've seen is this 26 femtoseconds that was listed as a Whistler measurement, and accompanying that was a 38 femtosecond frog measurement. So in those measurements, I think the computed 200 terawatts is a highest level, and so when you saw on the grid there was a less than 200 terawatts, it takes into account the fact that we don't have a full measurement, for instance, of radial pulse delay, which could affect the ultimate intensity on target. But the computation of radial pulse delay is at the 2 femtosecond level that Louise mentioned. We have one more question about what is the range in spot size in target area 2 and target area 3. So for target area 2, we still are setting up to achieve the full light into target area 2 we're anticipating getting sub a couple of micrometers. I think that would be fair to say. In Hercules, we've previously achieved sub
well, of the order of a micrometer diameter. In target area 3, with the F20 or F40 young, this is probably a question you might be able to answer. I don't know if you're there.
Yeah, for F20, I think we have pretty confident good focus photo is spot size of 20 micron for half maximum. For F40, I would expect it's the same as the F number, but we will see.
And then for sharper focuses, is there any other sharper focusing optic for F3 or for TA3?
Not
It's
right now.
f1.5, so you'll get
Yeah.
below 2 microns. Target areas, they have deformable mirrors, so should be able to get very much diffraction limited focal spot with tail ratio of 80% or better.
Each of the target areas has its own deformable mirror for each beamline, so that we can correct for wavefront aberrations locally to the focusing optic.
And the laser lines, both the petawatt and half petawatt compressors have their own deformable mirrors as well, so that the beam that goes to the deformable mirror, the beam that goes to compression, should be as flat a wavefront as possible to improve the compression quality.
Any other questions? I can perhaps, I've recorded them so far, but I might stop the recording in case anybody has a question they want to ask offline. So I'll stop the recording.